Okay, so here's the plan. Here are these two processes running away. So I'm going to start off, I'm going to be running in process 0, and at a certain period of time, right here, this magic moment in time. So time is sort of going down the screen. In this particular case, it's virtual time. So this notion of time elapsing in process 0. It suddenly gets to the end of either it goes off and asks the kernel to do something, say, get me another byte from the file, or perhaps a little timer goes off, a hardware timer saying, your time is up, ding, and your fraction of a second that you get to use the CPU is up, and I'm going to interrupt the running of this process, and we'll talk about how interrupts work at the hardware level in just a second. But there's some way of basically suspending execution of that guy. And this guy may not know about it at all. He just says, I want to do an add. You say, stop right there. I'm going to transfer control to the operating system. In step 2, I'm going to transfer control to the operating system. And in step 3, what I'm going to do here is to start saving away all that state information. So I'm going to take the physical registers that were being used by process 0, and I'm going to start copying them into a kernel data structure. Sorry, bang, bang, bang. So I'm going to have a special array in the kernel, which I'm going to call user. And one of the things that's in the user array is a copy of all the user's registers, R0 through R30. We don't actually need to save R31 because, of course, it always reads as 0. And there may be other things besides that, which we'll talk about here in the user data structure. Okay, is everybody happy with that? So I'm going to take the contents of the actual hardware inside the kernel here in step 3. There's actual code that's saying move R0 into location 0 of this special storage array. So I'm moving them into locations into main memory. So I'm basically copying everything out of the hardware registers. And then what I'm going to do is to put new things. I'm going to go to a different user structure. So this might be for process 0, and if I have the same user structure for process 1, I can basically go get all that information that just like the stuff I saved away for process 0, I'm going to go retrieve it for process 1 and put it back into the hardware registers. So do you see how we can sort of make it so whenever a particular process is running, when it looks in the hardware registers, when the process says R0 in an instruction, and you actually go to the register file, it will find the thing that it put there. Right? The fact that some other process sort of ran in between when it put something into R0 and then when it read it out, because we interrupted the execution of the program, that's okay because we've carefully saved away what somebody else did to R0 and restored what your contents were. So we're sort of playing this shell game, right? We're interrupting one process, and typically we say, okay, we're going to return from the interrupt and resume execution. In this particular case, what we're going to do is actually resume a different process. We're going to start a new thing running over here in step 5. And you can see process 1, which was halted at a particular instruction, starts by executing that instruction, and all the register contents are just what it expects to see, and it gets to run for a while. So we sort of have this dovetail picture here, where each process feels it's running, but between any two instructions, all of a sudden, a fraction of a second goes by between one instruction and the next as we go run some other process. And that's what's happening on all your machines now. Yes?
It seems that all of this will slow your down to crawl because you have continuous reads and writes and reads and writes.
Right, so let's just think a little bit about that, okay? So how many instructions does it take to take all the registers and store them into locations in main memory? So I need a store instruction. Store R0 into a particular memory location. So I might need 30 or 40 instructions to save away all this information. And it might take me 30 or 40 instructions to copy that information from another block back into the hardware. So it might be that saving stuff away and restoring might take 100 instructions or 200 instructions. Okay, if I give you, several thousands of a second to run, I'll say 10,000ths of a second. Okay, so your user program is how long, many instructions. So you're executing 1 billion instructions in a second. So if I give you a tenth of an you've run 100 million instructions. Right, so 100 million instructions, and then I'm going to take several hundred instructions to switch to another process. So even though the overhead seems large, actually it's a pinprick. I mean, you'd hardly notice. And the advantage you get is you get this illusion of running all the processes at once. And actually, they're each running for 1/10 of a second at a time. So let's just stop for a minute. Does that overhead seem large or small? Yeah, so I mean, the idea is that, particularly with these fast machines, that the context switches are really, I mean, there's a small cost that you're paying, but it's a fraction of a % of the total horsepower of the machine.
It just seemed that we were losing all the benefit of all the cache architecture and all that fast memory.
Right, and one thing you have to worry about is if I keep switching and I keep blowing what's in the cache, and then I have to spend many cycles reloading the cache. And so that's where we were starting to talk about, perhaps figuring out how to share, the contents of the cache physical memory, not virtual memory. So as I switched from virtual memory to virtual memory, I actually arranged the MMU and the cache to run in parallel. There was a slide at the end of last lecture that talked about that. And so, yeah, there is some loss of cache coherency, but it takes, out of the 100 million instructions that you're running, again, it might take you a % or two to sort of reload the caches. So it's a price that we pay. So we're paying a tax, but the tax is small compared to the benefit. Yes?
Where are we storing this user data?
I'm going to get to that. Okay, I'm going to show you some actual code here that will show you where we store it. Okay, so we basically are interrupting one process and returning to another process.